start presenting your name here.
Okay, thanks everybody for having me here. My name is David Coleman. I'm the Senior Technical Evangelist for Aerohive Networks. If you're not familiar with Aerohive, we're a publicly traded cloud-based networking company with a distributed architecture. Our main forte over the years has been cloud networking. The first two Wi-Fi companies to do cloud networking were Aerohive and Meraki, actually at the same time. And we were the first Wi-Fi company to offer a controllerless distributed architecture. So we've kind of been the market leaders in that. We're a publicly traded company for the past 4 years. And we're not just a Wi-Fi company, though. We're a cloud networking company. We also have switches, branch routers, and so on. I am CWNE number 4, and it looks like the slides are a little discombobulated, but that's okay. If anybody doesn't follow me on Twitter, I'd love for you to follow me on Twitter. My Twitter address is @MrMultipath. And if you're not already familiar with this, the Wi-Fi community is very active on Twitter, so it's a great way to actually learn and communicate globally with people in the Wi-Fi community. So I encourage you, I know that sounds strange, but it's actually a great way of what's going on in Wi-Fi. Follow a lot of the Wi-Fi leaders. Next slide, please. Quick plug for my book. I'm also the co-author of the CWNA Study Guide, which stands for Certified Wireless Network Administrator. If you're not aware, it is a vendor-neutral study guide for anything and everything to do about Wi-Fi technology or 802.11 technology. It is a certification test, and it is a study guide. This is the 5th edition of the book. It just came out a month ago. Even though it is a study guide, I would say about 80% of the people that buy the book buy it more as a reference guide. And our publishers tell us it's the best-selling Wi-Fi book in the world. It sells about 5,000 to 8,000 copies globally. And if anybody's interested, the easiest way to get it is on Amazon. And I just, if you bought one of my books in the past, thank you very much. Next slide.
So we have someone with your book here. It's really thick, man.
Oh, look at that. Yeah. So, if you stand on that, you'll be about 3 inches taller. And it also makes a really good doorstop as well. There you go.
It does.
So, yeah, it is rather thick. So we like to call it the Wi-Fi phone book because it's as thick as a phone book. So thank you once again for that purchase. I just made $1 American. So next slide, please. Okay, so what we're here to talk about is 802.11ax, and I know some of you have seen some of these slides and some of these presentations at other events. I mix this up a little bit differently at each event. So if some of you were at CWNP last week, you maybe saw a third of these slides, but I have more time today, so we're going to be able to see more. I could talk about 802.11ax for 4 straight hours, but since we have 55 minutes, let's just jump into it. I'm assuming everybody here in the room is familiar with the alphabet soup and how the 802.11 standard gets amended. And where we're at right now is 802.11n and 802.11ac. Wi-Fi has been around for about 20 years, and the N and AC now is the technology that's been here. N was introduced 10 years ago, AC 4 years ago, they introduced physical layer and MAC layer enhancements to achieve higher data rates and bigger channels. And hopefully everybody in this room knows that Wi-Fi operates at layer 1 and layer 2 of the OSI model. And so over the years, the IEEE has been defining physical layer and MAC layer 1 and layer 2 enhancements to make the technology better. But the main focus has always seemed to have higher data rates and also bigger channels. And so the analogy I've been using is bigger highways and faster cars. So next slide, please. So I've been to Brazil, and it kind of looked like this. I remember I was in a traffic jam once. We had to get from like one side of the city to the other in St. Paul, and it took like 3 hours. Um, and it's the same thing where I live in Atlanta, Georgia. We have too many cars and traffic jams, and the governments keep building bigger highways, and people, but more cars keep coming. So it hasn't been a very efficient use of the traffic. There's not an efficient traffic management system or transportation system in most of the United States, and in other countries. In some countries, they have pretty good transportation systems, but where I live, they don't. And if you get a crash or collision, then you get entire gridlock. Next slide, please. So what we need in both industries, both in the transportation industry for automobiles as well as Wi-Fi, is we need better traffic management. So about 2 or 3 weeks ago, I was in Las Vegas speaking at a Juniper Networks conference. And there was a partner there that is doing a big government-sponsored project in the state of Colorado and the city of Denver to have a intelligent traffic management system where all the streets and street lights and traffic signals communicate with all the automobiles and use that data, and all the automobiles can actually talk to each other. So it's kind of a very smart technology, intelligent, high efficient traffic management solution. And of course, you also hear all the press about the autonomous automobiles where they're going to be driverless and self-driving cars. We're on the cusp of that technology. I think we will see it in our lifetime. And we really need something like this for Wi-Fi as well, because Wi-Fi has not been very efficient. Next slide. So one of the things that I'm sure all of you know is that RF is a half duplex medium. You can just click, please. And at any given time, only one radio can transmit on a frequency domain channel, which is a frequency domain is a fancy name for a channel. So everybody takes turns, and everybody knows this. It's just the way RF works and the way Wi-Fi works. And because of that, because you might have 50 clients communicating with an AP on the same channel, there has to be some sort of mechanism so that everybody can take turns. So the IEEE protocol that's defined for this is called Carrier Sense Multiple Access Collision Avoidance. And that protocol ensures that everybody, it's a pseudo-random protocol, but it ensures that everybody gets a shot on the medium, but everybody has to take turns. That in itself is the part of the problem, because the protocol itself is not very efficient. Next slide. So everybody knows this, hopefully in this room should know this as well, but a lot of people don't due to marketing hype by Wi-Fi vendors. And that is that data rates, the advertised data rates that you see, like 300 megabits per second or 600 megabits per second for Wi-Fi, that is not the same thing as throughput. The medium contention protocol that we just spoke of, CSMA-CA, consumes the bulk of the available bandwidth. So in a legacy ABG environment, 40 to 50% of the data rate might actually be TCP throughput. And current technology, 802.11n and AC, excuse me, in pristine RF conditions, you might see 60 to 70% TCP throughput of your advertised data rate. Now, that's pristine, and that means ideal conditions, and that's basically laboratory conditions, meaning one AP and one client. You might be able to see that. So just a good rule of thumb is whatever your advertised data rate is, your aggregate throughput's going to be about half that. And then keep saying aggregate because this is a shared medium, and not all clients have the same data rate and throughput capabilities. Let's move on to the next slide. And it gets even worse. So we have a Wi-Fi traffic nightmare. Wireless is actually pretty resilient, all things considered, and it still works pretty good, but it's not as efficient as it could be. And there's kind of been a wrong focus by the IEEE. The IEEE in the past has just been focused on let's increase the speeds and have bigger channels. And that hasn't really made things better for the Wi-Fi traffic nightmare that we have, mainly due to the high density of clients. So almost everybody now has some sort of expectation of connecting at least 2 or 3 devices to a corporate network or enterprise network, not just their laptop, but their smartphone, their tablet, and then maybe some other device. And then I know IoT is an overused word, but the IoT in Wi-Fi is exploding exponentially each year and is growing. The numbers that are projected by 2025 are astronomical. So when you get more clients communicating with an AP, the efficiency of the MAC sublayer actually begins to drop. So, and that actually adds to medium contention overhead and gives you an increase in collisions. So once again, just the way Wi-Fi works, because it's a shared medium in the medium contention protocol, that in itself makes it kind of inefficient. So the question is there a better way to do this? Next slide. Another problem too is, here's another part of the Wi-Fi traffic nightmare problem and why Wi-Fi is not efficient. The bulk of data frames are small. And, you know, we are starting to see bigger data frames because more and more high bandwidth applications are starting to find a way in Wi-Fi, like a high definition video. But on average, if you average it out, Wi-Fi is very bursty, and you average out all the different kind of communications like email and just browsing the web, and you put it all together, the bulk of data frames sent by clients and up to APs are under 300 bytes. And so the result is extra medium contention overhead and MAC layer overhead. So for every single frame, you have to add an extra header and an extra trailer, and every single small frame has to contend for the medium. Even if you have frame aggregation, which is available to us within an AC, a lot of applications can't be aggregated. They have to basically just be sent one frame at a time because they have to be sent in a serial fashion. Perfect example is video streaming and voice. So that contributes to the overhead because everything has to be sent. And then once again, those packets are very small. So just the fact that the type of data that is being sent and you have to contend for the medium for each small frame is part of the problem. Next slide. Okay, so what's the solution? So the future, and it's actually the future has already started right now because APs are already shipping, is 802.11ax. And I'm sure you've heard by now, 802.11ax is the IEEE amendment for high efficiency. It hasn't been ratified yet. It's going to be ratified late next year. But the Wi-Fi Alliance has already defined a certification for it, and wireless LAN vendors are already shipping APs, including Aerohive, because the chipsets are already here for APs. You can go ahead and go through the bullets. Go ahead. Thank you. So the enhancements for AX isn't about better data rates. It's all about using physical layer and MAC layer enhancements for better traffic management. That's the goal. We need better traffic management, a better use of our existing resources and our existing frequency. And the goal is to increase average throughput by 4 times. You know, we're not going to get that goal right away, but by using some of these AX mechanisms to make things more efficient, we don't necessarily have to increase data rates, but if we can find a more efficient way to communicate on the channels we already have, we can increase throughput. Unlike AC, This technology will be defined to operate on both the 2.4 band and 5 gigahertz band. And I would imagine eventually they've announced possibility of Wi-Fi operating in 6 gigahertz, so maybe in the future 6 gigahertz as well. One of the reasons they're opening up 2.4 is that the chipset vendors want there to be more IoT devices. And so there's several things in AX that have been defined very specifically for IoT, and we'll talk about that. Next slide. So we're actually going to talk about all of these. There's something like 79 new things defined in the new IEEE standard. But you'll note, and I'm going to talk about all these right here this morning, but the main one we're going to talk about next is OFDMA, because it is our feeling here at Aerohive, as well as most of our competitors, that OFDMA is what is going to give us the best higher efficiency and the biggest bang for the buck. So next slide. And you can keep going. Okay, thank you. So I think this is an important slide, and I'm just going to read this definition, the definition of multi-user. And so the term multi-user simply means that transmissions between an AP and multiple clients can occur at the same time, dependent on the supported technology. Now, why do I define this in every presentation that I do about 802.11ax? The reason I'm defining this term is there's going to be a lot of confusion, because there's actually two multi-user technologies defined in AX. One is MU-MIMO, or multi-user MIMO, and some of you are already familiar with it because it was first defined in AC. Multi-user MIMO hasn't really panned out very well in the real world. We're going to talk about that. But there's another multi-user technology that's defined called OFDMA. OFDMA is what we think is going to provide the most benefit to everybody. But they are two completely different technologies, but they can both work in 802.11ax radios. As a matter of fact, they could actually both theoretically work at the same time. But we'll see about that. I think more than likely it's going to be one or the other in most cases. And in most cases, it's going to be multi-user OFDMA. Next slide. And next slide. Okay, so currently, here's what we have now. So everybody should know that the technology we've been using for the last 15 years is a modulation technology that's been used in a lot of RF technology, not just Wi-Fi, and that is OFDMA, orthogonal frequency division multiplexing. So within an AC and G and A, we'll take a 20 megahertz OFDM channel and divide it up into 64 subcarriers. Some of these subcarriers are used for management, which they're used for synchronization purposes between a transmitter and receiver, but about 56 of them can actually carry data simultaneously, okay? And the subcarriers are orthogonal to each other so they don't interfere with each other. So I'm getting a little bit of feedback there, but I'll keep on going. The main point I want everybody to know is that currently with this technology, it's single user technology, meaning that when a radio is transmitting, it's using all the subcarriers on that channel. Next slide. All right, so let's just I'm going to just say click. So just kind of stop right here. Here's how the technology works. So right now you have in the x-axis you have time, and the y-axis you have the channel width. Let's pretend that's a 20 megahertz channel, and those are your 64 subcarriers. You can go ahead and click. So right now, if client number one wants to transmit on current technology, it has to use all the subcarriers of that 20 megahertz channel. Click again. And client number two, same thing. When client number two wins a transmission opportunity and wants to transmit, it's going to be a single user transmission of using all the subcarriers of the 20 megahertz channel. And you can just click through the rest of those. And what you're seeing with this animation is that each time a radio transmits, it has to use all the subcarriers. It occupies the entire channel, including the AP. Next slide. So one thing that has changed now is there's a new technology called OFDMA, and it's not really new. It's been around for a while, and it's just an enhancement of OFDM. It's a multi-user version of OFDM. Don't get too caught up in this slide, but one of the changes is that there's in a 20 megahertz channel, the subcarriers are actually smaller now. They're 78 kilohertz in size, and there's now 256 subcarriers as opposed to 64. Sometimes subcarriers are also called OFDM tones. Just using the smaller subcarriers alone will give us about a 10% increase in efficiency. Next slide. So we're going to do the animation again here. Go ahead and click once. All right, so imagine this. So this is OFDMA. With 802.11ax. This is a multi-user version of OFDM. What if, let's just talk downlink for now. What if an AP wanted to transmit to two clients simultaneously? What it could do is subdivide a 20 megahertz channel into two halves. In matter of fact, maybe it could give half the subcarriers to client 1 and half the subcarriers to client 2, which it effectively would be about 10 megahertz to each client. So I like to call these baby channels, but the goal is just to send this data down to multiple clients at the same time by subdividing the channel. Next, click again. What if we could do this? What if the AP could say, you know what, why don't I allocate the channel to 4 clients? I'll give each client about 5 megahertz of frequency space and transmit data to just using those subcarriers on that channel to client number, that sub channel to client number 3, and then have different subcarriers for client 4, 5, and 6. You can just click through these a couple times. You could use the entire channel, or you could subdivide it in half again, or you could use the entire channel again, or you could do different combinations like you see right here. Like maybe I could give 5 megahertz to each client, and then 10 megahertz to client number 6. These subchannels, or these groupings of OFDMA subcarriers, have a technical name. They're called resource units. Next slide. Excuse me. So this is actually straight out of the standard. This shows how, pardon me, this shows how a channel can be subdivided for 20 megahertz. And those numbers there represent different amount of subcarriers. So you can have a resource unit that is 106 subcarriers. You can have a resource unit that is 52, one that is 26. Theoretically, an AP could communicate on a 20 megahertz channel with 7 clients at the same time. Pardon me 1 second. I apologize, I'm battling a cold. Next slide. So based on the multi-user traffic needs, the AP actually decides how to allocate the channel. So that's one thing that's different now here than what we've had in the past. The AP is actually kind of in charge when the AP is one control of the medium. And as you can see, this 20 megahertz channel can be divided up into 9 users, 4 users, 2, 1, or actually different combinations. So it doesn't have to be just 9, 4, 2, or 1. It can be different combinations of these resource units for either downlink or uplink communications. Next slide. So that first bullet's actually pretty important. So one thing you need to understand about this that a lot of people don't understand is CSMA CA still works. So the rules of medium contention still apply. meaning that the AP must win a transmission opportunity for either OFDMA, downlink, or uplink communications to occur. So, so what I mean by this is there's backward compatibility. So legacy clients can still get on. So legacy clients might win a transmission opportunity, and when the legacy clients win, they are transmitting on the whole channel. But when an AP wins the transmission opportunity, the AP controls the medium and can divvy up the channel and divide it up for either downlink or uplink. And so it's up to the AP. Next slide. So this is downlink OFDMA. So I'm just going to talk through this and then I'll have you run the animation. So what happens is both uplink and downlink, there's something called trigger frames. And the main purpose of the trigger frames is for the AP to tell the clients what resource units to use, how to allocate and divide up the channel. That's the main purpose of the trigger frames. There's like 9 different kinds of trigger frames, but let's just explain this pretty fast and simple at a high level. So when an AP wants to do downlink OFDMA and he wins control of the medium, the AP might send a multi-user RTS trigger frame. Now that does 2 things. Number one, it's an RTS-CTS process, so it uses the duration ID to clear the medium, including for the legacy clients, and tells everybody to shut up until the end of the frame exchange. But also in that first trigger frame is an RU allocation information at both layer 1 and layer 2. So the AP is basically telling 4 AX clients in this example, hey guys, I want you to know that I'm gonna send you information, but I'm gonna do it only on part of the channel. And this is the channel, part of the channel, the resource unit you need to be listening to. Once they get that RTS frame, the AX clients respond on their assigned resource unit with a CTS frame. And they all say, okay, good, send it. And then that's exactly what happens. The AP transmits on the whole 20 megahertz channel, but divides it up. And in this case, each client was assigned 1 resource unit of 52 tones or 52 subcarriers. And then once they receive that, they all send a block ACK. Now, let's go look at the next slide and take a look at this again through an animation. So the AP first sends this trigger frame, and just keep clicking, and the trigger frame tells them what resource unit to use. Once they get that trigger frame, they all send a CTS. And that clears the medium, and then the AP divides up the channel and sends them down their data on their assigned resource units, and then all the stations will send a block ACK. Now, the whole point of this, now think about how much more efficient this is, okay? Before, with what we're using right now, an AP would have to go to each of these 4 stations, data ACK, data ACK, data ACK, data ACK. Now the AP can just send them all 4 of their data at the same time. So that's less airtime that is consumed. It's more efficient, which means we're going to get better throughput. It's the same channel size, but it's a more efficient use of our existing frequency space. The other thing I want to bring you back to was, remember I said most of the frames were very small and under 300 bytes? Do you think you need a 20 megahertz channel to modulate a 300 byte packet? The answer is no. You can get it done with a lot less subcarriers. So it's been an inefficient use of the medium to use a whole 20 megahertz channel to send a packet that's only 300 bytes. So if we could send 4 packets that are 300 bytes to 4 stations at the same time, during the same time, that's a more efficient use of the medium. It's less airtime that's consumed, and you're going to eventually have better throughput. Next slide, please.
Hey, David, just one question. So if you do a parallel of what you're showing here with what we used to have before with 11AC multi-user MIMO on downlink, in AC we still use the whole channel, right? But to discriminate the data between the different users, we just use like a RF technology. There was nothing in the layer 2 protocol stack as you are describing here to allocate different subchannels, right? So how do you compare and contrast the downlink multi-user from MIMO?
All right, so I have a few slides on that, but I'm going to go ahead and answer the question because
right.
it's a fair question. So I mean, it's really good point actually. Here's the thing. First of all, you should know that this information is the RU allocation information that divides the channel is actually sent from the AP to the clients at both layer 1 and layer 2. There's bits in the PHY header that assign RU allocation, and then there's also a field in the frames at layer 2. There's an information element field that actually does the RU in the trigger frames that also assigns the RU allocation. So if they miss the information at layer 1, they also get it at layer 2. The difference between this and multi-user MIMO is simple. This is dividing up a channel, okay, and giving it different amount of frequency space. With multi-user MIMO, you're using the whole channel, but you are using you're sending unique, independent streams of modulated data to different clients. So you have to use the entire channel, and you're sending using different radio chains to send different streams and independent streams of modulated data to different clients. I'm going to circle back to multi-user MIMO here in about 4 slides.
All right.
But good question. But they are very different technologies. Next slide. And keep going. Okay, so quick, yes, right here. So quickly, here's uplink multi-user MIMO. So this is more complex. Uplink multi-user MIMO is going to require multiple frames. So the main thing is you're going to need is a buffer status report frame, a polling frame, and a report frame. So the AP, if it's going to synchronize for uplink transmissions, the AP has to ask the clients, what do you have to send to me? So it'll send this polling frame called a buffer status report polling frame that says, hey guys, what do you have, how much data you have, and what QoS access category it is. Then they'll all respond with what's called a buffer status report, and which tells the AP what kind of data they have. Once the AP knows that, he can then go through an RTS-CTS process and then send a final trigger frame. The final trigger frame basically does a couple things. It tells the clients what resource units to use, what transmission power to use, how many radio chains to use, what data rate to use, and it triggers them to all transmit at the same time right now. And then synchronized, they send uplink using their assigned RUs up to the AP, and then there's a block ACK. So why don't you just run through that animation on the next slide real quick, and you can just keep clicking. So once again, the first trigger frame is a poll saying, what do you got? The clients then will send, this is what we got. The AP compiles that information, sends an RTS to clear the medium, and then a CTS is sent up by the clients. And then a final trigger frame is sent down to do the RU allocation, and then it triggers the clients to send their data in a synchronized fashion using their assigned RUs at the same time. And then the AP has to send an ACK to them. Now this is pretty cool because we've never had any kind of synchronized uplink communications before. And we've never divided up the channel before. That's what's different here for both downlink and uplink as opposed to multi-user MIMO. We're cutting the channel into pieces, but we're also synchronizing this for uplink. And that's another difference between multi-user MIMO. There's currently there's no uplink multi-user MIMO. Next slide. And this you were asking me about the RU allocation. This is actually showing you how an AP would assign this information at layer 2 and actually assigns very specific subcarriers. Next slide. And then based on that information they get, they know which subcarriers and which RU units to use. So that information is relayed at layer 1 and layer 2 to the clients for both downlink and uplink. They have to be told what part of the channel to use. Next slide. And we'll just keep going. Next slide. Keep going. I'm going to have to speed it up here due to time. So this brings me to multi-user MIMO, which was the question that we just had. So multi-user MIMO requires spatial diversity. It's not about dividing up the channel. It's about sending independent, unique streams of data to different clients. Next slide. The problem is that it was introduced with AC, but currently hardly any multi-user MIMO clients even exist in the marketplace. There's about 4 or 5. The other problem is it requires spatial diversity for it to work, meaning that you have to have about 15 to 20 feet of distance between the clients, as well as distance between the clients and the AP. That is not conducive to most modern day deployments of Wi-Fi, because due to the high density environments, people don't have that kind of spatial distance. Multi-user MIMO works in a Faraday cage, but it hasn't really panned out yet in the real world. You can go ahead and click again. And another thing is they're also talking about enhancements. So they're talking about cutting down on sounding frames to try to improve on that. So they are talking about multi-user MIMO enhancements. But once again, we'll see. You still are going to need spatial diversity for multi-user MIMO to work. They're also talking about uplink multi-user MIMO in 802.11ax. You will not see that in the first generation of chipsets. I am not going to bet my money on multi-user MIMO with AX because it hasn't worked for us yet in the real world. So I'm not thinking it's going to work with AX at least immediately. I hope it works. I hope it gets better. But right now, multi-user MIMO, the conditions for it to work just don't really exist in most Wi-Fi deployments. So you will see the technology, you will see enhancements in AX chipsets, but everybody believes that multi-user OFDMA, by dividing the channels, is a better way to go and is what is going to give us the most and better efficiency. Next slide.
So,
and I hope, go ahead.
One of the things that frustrates the whole, industry is exactly what you're describing, like the promise of a technology like the multi-user MIMO. So with the multi-user OFDMA, we can be sure that this will gonna be available now in the first phases of the AX, right?
Yes. So multi-user OFDMA will be a requirement. It is in all the new chipsets, and the Wi-Fi Alliance is going to require both uplink and downlink. Okay, so it will be required. There will be requirement for downlink multi-user MIMO. You will not see the uplink multi-user MIMO. Let me reword the question. It's frustrating because the question I get asked all the time is, how do we know this is actually going to work, the multi-user OFDMA? And the bottom line is, until it's field tested, we don't know 100% that it'll work. But here's why I'm confident. Everybody has a cell phone, right? Everybody has one of these. If you have one of these, you are already using OFDMA because LTE downlink uses OFDMA. It is a field-tested technology, okay? Just with another type of RF. So that's why we're confident it's going to work real well with Wi-Fi as well. But once again, until it's field tested, we can't be 100% sure. But I'm much more confident about multi-user OFDMA than I am multi-user MIMO.
All right, thank you.
Okay, next slide. We're going to have to go through this real quick because I'm running out of time. Next slide. Just skip this slide, skip the next slide. and we'll go right here. So one of the biggest problems we have in Wi-Fi is co-channel interference, and it's because APs and clients hear each other. You can just keep clicking. It's impossible to prevent CCI in 2.4 gigahertz. Keep clicking. And the number one cause of co-channel interference is clients. Now, you can prevent co-channel interference, and all co-channel interference is APs deferring because they hear each other, or clients deferring because they hear each other on the same channel. It's impossible to prevent on 2.4 because there's only 3 channels. In 5 gigahertz, if you're using lots of channels and you have good design, you might be able to prevent it. But this has always been a big design problem. It's because of the sensitivity clear channel assessment thresholds. Clients defer when they hear each other on the same side, on the same channel. So next slide. So what BSS color combined with something called spatial reuse operation is a way to hopefully solve this problem. I don't think we're going to see this right away, but it is available in the chipset technologies. It might take a while before we actually see this finding its way and working in the field. But basically, all BSS color is, it's a numerical identifier to identify different basic service sets of APs and clients that are on the same channel. And the hope is this, by being able to distinguish between different basic service sets, you might be able to apply adaptive spatial reuse thresholds to maybe ignore an AP and clients that are very, very far away on the same channel and still be able to transmit it at the same time. Next slide. And next slide. And just hit this animation. So what it's the goal is if you can distinguish between different basic service sets, radios could adapt their signal detect thresholds to be less sensitive or more sensitive to different basic service sets on the same channel. And the goal is hopefully maybe you might not always have to defer, and maybe you could transmit at the same time. But this is going to be tricky because you don't want there to be collisions. So many of you might already be familiar with something called receive start of packet. It is a setting that you can adjust on some APs to adjust the sensitivity thresholds on APs. This is sort of a dynamic version of that, and it would be based on the BSS color information. So Wi-Fi geeks like us get very excited about this because this has the potential of dynamically fixing CCI problems or OBSS problems. But once again, I think it's going to take some time. But this is one of the topics that a lot of people are very interested in, at least from the Wi-Fi community, because it's directly addressing that with adaptive thresholds. Next slide. So
the BSS coloring is something that is going to come in the frames itself, frame by frame, or
once again, this information will be relayed at layer 1 and layer 2. So it'll be in the PHY header, okay? And it'll also be in a field in an information element in control frames and management frames.
All right.
Yes, a lot of information in AX is relayed at both layer 1 and layer 2. Let's keep going. I'm going to skip some slides here in the interest of time. Target wake time is just a something that's been defined for IoT. That is a negotiated exchange between a client and an AP where a client can say, I'm going to sleep for an hour. This is meant for to save battery life. Next slide. So I think you're going to see this, believe it or not, and this will be more efficient because it'll cut down on overhead and it'll also save battery life. Client devices could literally have a targeted time where they're going to say, I'm going to wake up in 2 hours. But it is a negotiated frame exchange between the AP and the client. They have to agree on it. Next slide. And there's also going to be a higher modulation, 102.4 QAM. I don't pay much. This is the one thing that will give us higher data rates, but guys, for this to work, you're going to have to be standing underneath the AP, and you're going to have an SNR of 35 dB. So once again, don't get caught up in higher data rates. It's more about the efficiency. Next slide. And keep going. We're going to skip these slides. And keep going. And keep going. Because I want to get to the real world stuff in our last 10, 15 minutes here. Keep going. All right. So the last part of the presentation is about real world. Let's talk about this real world. So go to the next slide. And this is the number one question I get. Is there any benefit for legacy clients with AX? And the answer is yes or no. So hit the bullet. And the first thing you should know is that legacy clients can't do OFDMA. So they will have to still use what they were using before, a full 20 megahertz channel. So truth be told, to take full advantage of AX high efficiency capabilities, such as OFDMA, you're going to need AX clients. Next slide. However, will there be benefit for AX clients? And the answer is yes, non-AX clients. Legacy clients will see benefit as AX clients enter into the client population. As they enter into the client population, there'll be multi-user communications, which frees up valuable airtime. And when it frees up the valuable airtime, that's more airtime for the legacy clients. So legacy clients will see a benefit as the AX clients start joining the client population. Next slide. Which gives me the biggest question right here. Where are the 802.11ax clients? There aren't any. We all know that. Next slide. But they're coming, guys. Keep clicking, please. They're coming. Broadcom, Qualcomm, Intel, they've all announced clients. Broadcom makes 70% of the clients that are in the smartphones and tablets. We think we're going to start seeing clients as early as Q1 of this year, maybe even Q4 of this year, maybe as but next year, you're going to start seeing clients, and your customers and employees are going to start bringing these devices into the workplace. And if you look at the projections over the coming years, the bulk of the clients that are going to be made are going to be AX clients. One thing I've learned in the industry is the chipset manufacturers drive this industry, and they are all coming out with AX clients very soon, and the bulk of them being 2x2x2. Next slide. I want everybody to know, if anybody tells you you need a 10 gigabit uplink between an AX AP and a switch, that's total nonsense. Most bottlenecks are at the WAN uplink. Next slide. But will we need multi-gig ports? Maybe. Probably eventually. In the past, you've heard hype that you need multi-gig, or that you're going to exceed, due to the greater bandwidth and the better throughput capabilities by the new technologies, that you're going to exceed 1 gigabit uplinks. As we start to see a lot of AX clients and client populations grow, it's probably going to happen eventually. It's not going to happen right away. I'm not telling everybody you have to upgrade your switches to multi-gig yet, but as I'm just telling you right now, every Wi-Fi vendor is going to start putting multi-gig ports on their APs moving forward for future purpose, for future proofing. Next slide. Next slide. The more important thing is going to be this, PoE. These APs are going to be 4x4x4. So the days of standard PoE are over. You're going to need PoE plus. It's just a matter of fact. To take full advantage of AX capabilities and 4x4x4 APs, you're going to need 25 watts or more. So PoE plus is a need, and you're really going to have to watch. So you may have to upgrade your switches if they don't have PoE plus, or if they do have PoE plus, you're going to have to carefully watch your power budget. So PoE power budget is going to be more important than ever. Next slide. And then some vendors have announced 8x8x8 APs, which means they're going to need a special power injector, or 45 watts per port. Even PoE plus won't power them. So you're either going to need to run 2 PoE cable runs, or you're going to need power injectors. So these things, these vendors that are coming out with 8x8x8 APs, you can't even power them with PoE plus. You're going to need a lot more power, so they're going to be beasts. You're going to basically need a power generator to power these big APs. So be aware of that. They're going to consume massive amounts of power. Next slide. And then the next question I get is 8x8x8 going to be better than 4x4x4? And so some vendors are coming out with 8x8x8 APs. There's two chipset manufacturers, Broadcom, which is what Aerohive uses. They're going with a 4x4x4 strategy. Qualcomm is coming out with an 8x8x8 for 5 gigahertz and a 4x4x4 for their 2.4. Is there any advantage for 8x8x8? Yeah, there is. Multi-user MIMO. If multi-user MIMO all of a sudden decides to work in the real world, with AX, there will now be a way for there to have 8 spatial streams, multi-user MIMO streams, at the same time. But once again, how well has multi-user MIMO worked out for us so far? It hasn't. So there's no real advantage when it comes to OFDMA when 4x4x4 versus 8x8x8. And there's already hype that you'll be able to have more clients on an 8x8x8 than a 4x4x4. That is absolute marketing nonsense. You'll have the same amount of clients. If multi-user MIMO starts to work on the client side, then 8x8x8 you'll see some advantage there. Otherwise, you're getting no real advantage other than your 8x8x8 APs are going to cost you more, and you're going to need more power. So you should be aware of that. Same amount of clients, whether it's 4x4x4 or 8x8x8. Next slide. So I got about 5 more minutes here. I got about 2 or 3 more slides, and we'll open it up for questions. Just know that AX or any new Wi-Fi technology does not mitigate bad design. You can keep clicking, guys. The design and validation are going to be important. Go ahead and click. You still need design and validation are going to be key, and everything's going to have to be field tested. So don't think that I've already heard people say that AX is, it'll just do everything for you. Anytime anybody says you don't need to design a network, they don't know what they're talking about. Design and validation are still going to be key. Next slide. And what about troubleshooting? This is going to be interesting because, this is still new technology. Right now, there's no clients yet, so there's no decoding of the data frames yet. But already the developer version of Wireshark can decode 802.11ax management and control frames. And a lot of you guys know Adrian, who makes the Wi-Fi Explorer for MacBooks. It can already decode AX management and control frames. Also, a spectrum analyzer can show you the resource units in a spectrum analyzer. That can already be seen. Next. And if you haven't heard, the Wi-Fi Alliance has announced a new naming convention for marketing purposes. So if you ever see Wi-Fi 6, that is the marketing name for 802.11ax. Next slide. And I want you to know that Aerohive is shipping. We already have 3 AX APs that we're shipping. I'm not going to go through the marketing spiel. You can check out and learn about them on our website. But we have 3 AX APs that are available now, and we can't keep them in stock. We're selling them like crazy, and they're all 4x4x4. Next slide. And here's some extra resources. You're welcome, by the way, guys, to have a copy of the slides that are being used today. You're welcome to distribute those as well. I want to encourage you to follow my blog series on AX. And if you go to that link down there, too, you can also download a little booklet that I wrote called AX for Dummies, and give them your name, and you can get the PDF for free. So that gives us about 4 or 5 minutes for questions. We can go to the final slide, which is the question slide, and hit me up with. I wish we had more. I wish I had 2 more hours with you guys, but I got 5 minutes. So hit me up with whatever you got.
Thank you, David. Thank you. Any questions, guys? for David.
Come on, I
So
know
what-
there's something.
Yeah, one thing that I think you hit pretty well is the 8x8x2 versus the 4x4 story. So what you were saying is that considering that the multi-user OFDMA is the thing which is mandatory and will be there, most probably, then the multi-user MIMO thing. So that's what makes you believe that the 4x4 is okay to have 4x4 instead of having an 8x8, right?
Absolutely. Look, if multi-user MIMO all of a sudden magically works and clients support it, there will be some multi-user MIMO advantages in high bandwidth, low user density environments. But that's not the way most Wi-Fi environments are, and most clients don't support multi-user MIMO. So, but that being said, people are still going to buy these 8x8x8 APs because they're going to see that and they're going to think, oh, 8 must be better than 4. And look, right now, Aerohive isn't coming out with an 8x8x8 AP. That's not to say we won't one day. But I can tell you right now, at this point in time, I see absolutely no advantage of 8x8x8 over 4x4x4, other than that you're going to be putting more money in somebody's wallet because it's going to be more expensive.
Other questions? So I'm gonna keep asking if there's no other questions. Yes.
Asking him if you have some example of this solution with IoT.
Did you get that?
Any examples with IoT?
Yeah.
Yes, together with AX.
Not yet. Not yet, mainly because there's no clients. But the clients are coming, and there's like 4 things in AX that have been put in by the chipset manufacturers specifically for IoT, because it's all about the chipset manufacturers want to sell more Wi-Fi IoT chipsets, but they got to get the price of those chipsets down so it can be competitive with BLE chipsets and Zigbee chipsets. So one thing they put in is TWT that'll conserve battery life and be a cheaper, more affordable chipset. There's also something called 20 megahertz only mode that you'll probably see in IoT devices. So it remains to be seen, but the chipset manufacturers are being aggressive on that. So I think we will see it at the minimum TWT as a requirement by the Wi-Fi Alliance and in APs and hopefully in IoT devices, hopefully as early as next year. But I don't have anything real world yet. I'm just being honest.
And along the same lines, if you think about IoT and if you think about 2.4 in AX, do you foresee like laptop manufacturers or smartphone manufacturers using chipsets, AX chipsets that are going to be dual band, or most likely 2.4 are going to be for chipsets for IoT, and hopefully the laptops industry or smartphone industry are going to use 5 gigahertz only?
I think the laptop and the smartphones will still remain dual band, but with a preference towards 5 gigahertz. Most of the chipsets now in smartphones are dual band, and they're 2x2x2, and they already try to connect to 5 gigahertz first. They do band steering on the client side. That being said, I think the bulk of the IoT devices will probably stay on 2.4, at least for now. And in all honesty, we don't really want the IoT devices on 5 gigahertz. I'd rather them stay on 2.4. And maybe they'll find their way to a lower band eventually as well. But it's all about cost, and it's cheaper for whatever reasons to make the chipsets on the 2.4 band. And so that's why I think most of them will remain, the IoT devices will remain there. But that's also why AX has been brought back to 2.4. I've heard some people say that AX is going to fix the 2.4 band with, I don't agree with that because there's still only 3 channels. You know, BSS color has the potential to make it better. I think it's more about bringing AX to 2.4 for the availability of the IoT devices, and that's my opinion.
David, I have a question here. So right now we are on draft 3.0 for the AX standard amendment. And do you think that we are going to add any channels like they did for AC for channel 144, which they added for on that amendment? Do you think that they're going to add any other channels on 5 gigahertz band for the AX amendment?
No. I mean, anything can happen between now and then. But there's no reason this technology couldn't be ported to the 6 gigahertz channels that I don't know if you guys heard, but here in the United States, they announced yesterday that they're doing serious research on making 6 gigahertz available for Wi-Fi. And when that happens, then other countries in North and South America follow as well, and they all cooperate with each other. So I don't think by next year that'll happen, or I don't know if it'll necessarily find its way into the amendment, but the technology could be easily ported to 6 gigahertz. And if that does happen, say in like 4 or 5 years, then there will be no reason there could be like a second or third generation of chipsets that could support AX technology at 6 gigahertz. And what I think would be cool about that is then there's no backward compatibility because there's no older legacy clients. So there's no need for any of the RTS CTS overhead. So that's one of the kind of cool, exciting things about 6 gigahertz is we could use the newer technology only, and we don't have to worry about the old clients dragging everybody down. But I mean, that could be a whole nother discussion, but I think that's kind of what you'll see is I think you'll see AX technology at 6 gigahertz if we ever get the opportunity to use those frequency bands.
All right, thank you.
Thanks for your time. To respect your time, we're gonna shut it off now. Otherwise, unless you have more time for questions, but I really appreciate David.
Absolutely, it was my honor. Thanks very much, guys. I really appreciate you having me here, and you know, thanks for inviting me. And you know, it's been a while since I've been to Brazil. I hope I get back. My company is actually growing in the Latin American market. We have a SE director, Roger Finera. If you want to learn more about AeroHive, feel free to reach out to me or to Roger. And hopefully we'll find a way to get me down there in person here in the next year or so. So thanks again, guys, and everybody have a great day.
Thanks, David.
Okay, bye-bye.